Hi, my name is Jim Schier, and I'm with NASA's Space Communications and Navigation, or SCAN, program. I'll be talking about governance of communications, position, navigation, and timing, or CPNT, capabilities for the Moon and Mars. Communications here includes network layer services as well as regular link layer. So let's start with reviewing the topics I'll cover. I need to start by defining what's meant by governance in this context. But we also need to look at what's the current state of governance and who is studying governance issues. What are the major issues that have been identified so far? And then I'll segue to talking about Mars and how it differs from the Moon before providing some closing comments. We need to look at governance in terms of interaction and collaboration between different communities. We can define different communities in different ways, such as different countries, different organizations, different economic markets, but they all exhibit some competition versus cooperation. And if we're going to achieve collaboration, we have to find ways to work together and define the process and methods and tools that will enable us to collaborate regarding the shared context. So even though those communities have some unique capabilities, they also share some context. In this case, at the Moon, we're talking about peaceful purposes in space, registration of space objects, emergency assistance. If one of the spacecraft or crew members needs assistance, that's required to provide service. And then there are things that are specific to communications and PNT capabilities like spectrum. So we have to work on the definition of the frequency bands that we use, because we are using the same frequency bands for all of the different countries and systems that we're talking about. Space traffic management is another example where we have to worry about safety of navigation. We need to navigate a variety of vehicles in a similar location around the Moon and on the surface without running into each other. And that requires knowing when and where things are located. Along with this, we have to worry about the other general capabilities like interoperability and liability. But the best way I can summarize it is we have to figure out how to guide the evolution of international governance to be able to realize an effective LunaNet that provides CPNT capabilities and evolves into someday downstream a solar system internet. NASA is a member of a group called the Interagency Operations Advisory Group, or IOAG. IOAG is chartered to ensure or promote interoperability between the agencies' communications and tracking and now navigation capabilities, and so that we can better cross-support each other on our multinational missions. To do that, IOAG established a committee to study LunaNet governance and adopted a definition that says we'll do this for the collaborating communities to develop the shared principles, norms, rules, decision-making procedures, and organizations that shape the evolution of the system. This is actually based on the definition of internet governance developed by the UN at the World Summit in 2005. And it distinguishes between binding governance, that is, treaties, laws, regulations, and non-binding governance or technical coordination, which is typically on a best effort basis where parties can withdraw if they decide to. Bottom line is to have effective governance, we need to establish a threshold where we guarantee that our collaboration results in no harmful interference. So that we can work side by side at a minimum, and even better than that, interoperate where possible. So looking at the formal treaty level of governance, the UN passed the Outer Space Treaty in 1967 and elaborated on that in further treaties on astronaut agreement, liabilities, and registration over the next 8 years. those are the ones that we'll principally pay attention to. The Moon Treaty has not been adopted by enough states, and in particular doesn't include the major space powers. So we'll ignore that one. These treaties establish a set of requirements that define obligations, permissions, and prohibitions. So obligations are things that are declared by the treaty to be lawful and mandatory. You have to do them. Prohibitions on the other extreme are deemed unlawful or illegal and are mandatory. You cannot do them. And in the middle are permissions where things are lawful, but you don't have to do them. They're optional. You can decide. So some examples of obligations are bearing international responsibility and liability for your actions or those of your companies in your nation state, supervising non-governmental space entities like industry, avoiding harmful contamination as part of non-interference. And examples of prohibitions on the bottom are no appropriation of bodies. So you can't claim a celestial body or a part of it for a national use as national territory. Also prohibits weapons of mass destruction, military bases, and weapons testing. In the middle there, it allows you to do scientific research, to explore, to use outer space, to have free access to all celestial bodies for peaceful purposes. So that's a quick categorization there. Of course, there are a lot of details. Other rules start with the UN Charter itself. Another treaty was established for the International Telecommunications Union, the ITU, that establishes it as the legal binding authority for frequency management across the world. And then there are a variety of other international law categories that I won't go into. And below that are soft governance principles that have been established, such as the Artemis Accords, which has been signed by 59 states and establishes a set of non-binding principles on good behavior in space. Similarly, China has established, as part of their International Lunar Research Station program, cooperation through formal bilateral agreements with partners that can establish, as you see on the right, cooperation in various technical domains and at various levels, from individual equipment all the way up to systems level. The IPNSIG conducted a study a couple of years ago and published a report on the solar system internet architecture and governance that we collaborated on. This is a figure from that report that gives an overview of some of the agencies and organizations that are involved in this. Starts with, on the left-hand side, the not binding governance or space law agencies such as the UN that passed the Outer Space Treaty. COPUOS promotes the peaceful uses of outer space, and ICG, which is the UN's International Committee on Global Navigation Satellite Systems, which is not a regulatory committee, but does influence navigation satellite systems for compatibility in the terrestrial environment. In the middle, we see a big box around various space bodies that start with the space agencies on the middle left. The space agencies work on their own missions, but they also work with each other on bilateral, multilateral space missions. And that leads to a need for international bodies that help coordinate the efforts between the agencies, such as up on the top, the IPNSIG for space exploration, developing human exploration campaigns, the IOAG that does it for communications and navigation capabilities. And underneath that, in the middle, you see the SFCG that does frequency coordination, and CCSDS that does development of space data standards that are either developed by CCSDS or adopt or adapt standards from other standards organizations that you see down below in the green boxes for use in space. The IPNSIG, pictured on the right there, participates as well as part of the Internet Society and facilitates development of the SSI. So if I look at the two reports being done by the IOAG committee and the IPNSIG, we can see the principles established in those two groups. They're a little different in length, but they're actually quite consistent. And what I've done here is categorize them in terms of which of those principles imply regulatory or policy level binding governance, and which of those principles involve non-binding technical coordination. You can see that both of the groups emphasize the technical coordination, but both groups also necessarily involve some degree of binding governance. So with that, there will be convergence on these principles in the future as we work together. The IPNSIG report also identifies a set of elements related to governance that are worth mentioning. The policymaking process is done at several levels. So NASA can provide policy at the NASA agency level, but we also work at the national level to come up with U.S. federal government processes, and then work at the international level. So those policymaking processes occur at different levels and require coordination up and down at different levels of organizations. We have to manage critical resources. So some of these you recognize as networking capabilities like IP addressing and domain names. But some of these, like spectrum, require relate to the underlying physical layer and have to be coordinated at an international level to enable the higher level of networking to occur. Similarly, in standards, there are agencies that develop communication and networking standards, but there are also underlying needs for time and coordinate systems because a lot of applications need to know when and where you're located. So those standards are also part of the overall ecosystem. And then cybersecurity rears its ugly head here, and we expect that the vulnerabilities and problems we have with cybersecurity and the terrestrial environment will apply to us in the lunar environment as well, and similar capabilities will be needed. One thing that's missing from the report here is testing and calibration. These are necessary to ensure interoperability in an operational sense related to performance of the networks and the systems they serve. Switching for a moment to the PNT side, the three agencies that are most heavily invested in realizing LunaNet today are ESA, NASA, and JAXA, that are working together literally on a handshake agreement right now. So informal coordination and collaboration at the moment, but probably leading to something in terms of a more formal agreement that will eventually emerge. And they're working on interoperability specification that's about a dozen volume set of standards that are being developed right now. The other organizations in the round table here, some of them I just mentioned on the prior slide. The one in the lower left refers to the reference systems and time systems. These are the systems that you need on an international standard basis to be able to define time and coordinates for location and trajectory. And those are being worked through the science community, the International Astronomical Union, the International Association for Geodesy, International Bureau of Weights and Measures, and they are working on those underlying standards that we require that support what we do in communications and PNT. An example, we just recently held a joint cislunar PNT workshop sponsored by the ICG and IOAG and hosted by the United Nations. That brought together about 40 countries in an international setting where we could share information on frameworks and systems and ambitious plans that are underway, spectrum coordination, and governance were all featured as part of the sessions in that workshop. Bottom line was there was a great takeaway from this, a lot of cooperation, a lot of collaboration fostered, and the recognition of the need to work this on a steady basis. So you can see the list of agencies that are involved in this. It's a long cast of characters. that all have roles in this. The ICG is, as a result of this, now standing up a new lunar working group that will pursue this in more detail in cooperation with IOAG and other groups. But to look more at networking, we know that IP networking technology developed hand in hand with networking governance, but on a somewhat ad hoc basis because it was an unprecedented capability. Now that we have internet as a precedent to look at, we can look at the differences for doing solar system internetworking. And one thing we recognize is that space networking takes a longer time to set up systems and put it in operation. So we have to define more of the governance ahead of time as we're developing this before it goes in operation, and then evolve from there. Well, the characteristic that you're going to see that differs is that the things that we expect in the terrestrial networking, sources and destinations on the Earth, routers and servers and networks serving them, now picture all of those things on the moon or in orbit around the moon or to and from the moon, so that the community there is a cislunar community, not just an uplink and a downlink. That's going to require network-to-network interfaces in space, on and around the moon, and local network management, which drives you to identify some of the differences between networking capabilities that we have and what we need. What are the gaps? In particular, space communications is a highly scheduled activity. Things are on trajectories that are well defined by the force of gravity. And the result is missions that are complex, operate on strict schedules, and don't respond as much to demand access kind of real-time changes. But we'll have to accommodate that. Enterprise service management then expands to interagency and inter-service provider coordination, and has to be use the existing fora, but perhaps with some extensions. For example, we have 5 regional internet registries covering the Earth, but nothing covers the moon. Do we create a new registry for the moon, or do we build it into the existing registries? There are questions like this throughout the existing infrastructure. Time is a big factor to consider in this. We have a Earth standard called Coordinated Universal Time, or UTC. We do not have a similar time scale for the moon, but it is now under development by BIPM, and will run at a slightly different rate than UTC. So lunar time isn't exactly the same as Earth time. And that means we'll need standards for managing and distributing and synchronizing time between Earth and Moon and between network operators. It's also needed for the scheduling within a multi-service provider network of networks approach. And then security comes in with things like certificate authority on an intergovernmental basis. Peering policies. We have network operator groups, NOGs, for terrestrial. We may need the similar kind of thing for cislunar network operators, so that they can decide how to route data and support each other over cross links and space-to-surface links and surface-to-surface links that may introduce exchange points on or around the moon. We also have to prioritize traffic over highly constrained space links. And finally, we'll have to worry about the differences in network registries and coordination. So naming and numbering in space will be a little bit different than it is on the terrestrial environment. All of that can be summarized in terms of LunaNet being a set of cooperating networks that provide interoperable services for users on and around the moon. And the diagram on the right shows that you have blue links that connect the moon to the Earth. Those are the trunk links or the backhaul capability. But in the lunar environment, you then have network service providers with assets in orbit on the surface, talking to users in orbit and on the surface, providing those services so that the users can operate over short-range links or proximity links, and let the service providers handle the backhaul long link to the Earth. So how does this translate when we move to Mars? Well, pretty well. We can see that we've definitely set up the architecture so that LunarNet architecture can be applied to Mars in the future with pretty much the same architecture, and it's divided into two segments. In the upper right, we see the Earth to Moon or Earth to Mars links there, and the difference there is between a 400,000 kilometer link to the Moon versus a 400 million kilometer link to Mars. It's 1,000 times farther away. So yes, there are differences in the frequency bands and the protocols that will be used over those trunk links, but those will largely be used by the network service providers, and the user won't have to worry about them. What the user will see is at and around Mars, just like at and around the Moon, those proximity links then enable us to deliver services over short-range proximity links, and therefore the proximity service-based architecture of the Moon applies equally well to Mars, with, of course, adaptations. So if we look at the strategy, then it's clearly to maximize the commonality of standards for Moon and Mars over those proximity service links. Where the standards don't exist, the major investors, starting with NASA, ESA, and JAXA, will start developing core capabilities. And eventually, we'll start working with the standards organizations to roll those beginning rudiments out to standards organizations for more sustainable evolution over time. Frequency coordination is required. So the diagram you see in the upper right shows the lunar architecture for all the frequency bands used, and the diagram below that shows our effort to start looking at making the Mars frequency architecture look as much like the lunar architecture as we can, again, driving as much commonality as we can into the architecture. Beyond that, we expect to see a lot of participation from industry in this. More and more, we are picking up on industry standards such as 3GPP. So cell phone standards are likely to be used on the Moon and could then be used at Mars as well. We expect that this will operate over this coordinated capability, provide the user the appearance of a single system of systems with aggregate capability and performance that meets needs, with a lot of flexibility to provide cross support between agencies and between network service providers. All of this, of course, will take place over 20 years or more, so there will be incremental development and evolution of these capabilities. But the bottom line for governance, this is going to require a lot of collaboration sustained over a long period of time. We'll evolve from the ad hoc situation of informal handshake basis today to more formal agreements, leading to some changes in the formal binding governance as well. So to wrap it up, I need to point out that communications and PNT are essential infrastructure, going to space, going to the Moon, going to Mars, and it requires continued attention to governance. The good news is much of the framework for binding governance already exists for space, courtesy of the last 50 years, 60 years of UN work. Where we find ourselves short is on the non-binding governance side. So LunarNet, with new capabilities that's going to require new standards and new partnerships for collaboration, is driving the evolution towards as much non-binding governance as we can, because binding governance is harder to achieve. So we'll work on collaboration and cooperation to the maximum extent possible. And then recognize industry will play a growing role in this as we proceed. Last note, the U.S. federal budget is in work right now, but both the president's budget recommendation and the work being done in the Senate add explicit new funding for Mars communications So capability that we might have pictured as being 5 or more years downstream to worry about the Mars side has a serious possibility of coming into play next year. And then we'll be developing Mars and Moon governance in parallel, which is good news. And with that, I thank you for your time and attention.